again, not necessarily regular, but any language at all, we can define L0 as the language containing the empty string, and Li by induction as L concatenated with L to the power I minus 1, which is just another way of saying that you concatenate L I times. Okay. And then L star is the union of all these Li's for all I greater than equal 0, right? That is for all I belonging to the natural numbers, okay? In other words, this is L to the power 0 union L to the power 1, which is of course L union L square union L cube, and so on. So it's an infinite union, okay? And this, by the way, this star is called the Kleene star. And this is named after Stephen Kleene. He was a famous 20th century logician who laid the foundations of automata theory in the 1940s and 50s. And we also defined L plus, which is simply L star. Sorry, let me just write it this way first. So this is I strictly greater than 0, Li, which is L union okay, so we have seen all this. This is just by way of recap. So here's a question. Is it possible that L star equals L plus for some L? Is it possible? What is the answer? Anyone?
Sir, if epsilon is part of L.
Right. This is possible if and only if epsilon belongs to L, right? Okay. And now we come to a new definition, which will lead to a different characterization of regular languages. So far, we have characterized regular languages as those languages for which there exists a DFA or NFA or epsilon NFA, which accepts that language, right? So we have given characterization in terms of machines, but now we are going to give a different characterization, okay? For this, we need to define a new concept. So again, sigma is an alphabet. So the regular expression So given an alphabet sigma, the regular expressions over sigma and the sets they denote are defined inductively as follows. Okay. So on the left, we will define, let me use small letters here. We'll define the regular expression E. And on the right, we'll define the set denoted by the regular expression E. And this we'll call LE. Okay, so first of all, so this is an inductive definition. So we start with the base cases. The symbol empty is a regular expression, and the set denoted by this regular expression is the empty set. Okay. Two, the symbol epsilon is a regular expression, and the set or the language denoted by this symbol is this, the singleton set containing epsilon. If A is a symbol belonging to the alphabet, then A itself is a regular expression, and the set it denotes is the singleton set containing A, right? So it is looking rather boring so far, but these are the base cases or the base clauses. Now we come to the inductive part. If R and S are regular expressions, maybe I'm using a different kind of R there. So let me stick to that. Denoting sets or languages R and E. Sorry, R and S. Then the following are also regular expressions, namely R plus S within parentheses, and RS again within parentheses, and R star in parentheses. Well, we often drop the parentheses when there is no confusion. Okay, so these are also regular expressions. And what are these sets denoted by these regular expressions? Well, for R plus S, the set that is denoted is R union capital S. For RS, it is this is concatenation of languages. And finally, R star, which is the Kleene star. Right? So this is the definition. And let me just point out that what you have on the left side, that is the left column, is a syntactic object. To slide it down a little bit. So this is a syntactic object. What does it mean? Well, it's just a symbol, right? It's a symbol or a string of symbols. And on the right, what we have is its interpretation or semantics. So on the right, we have the semantics of the syntactic object on the left. So what is semantics? The meaning of semantics is meaning or interpretation, right? So we distinguish between the two. And although sometimes we use the same symbol, such as the empty set, right? When used as a regular expression, it's just a syntactic object, right? But its semantics is the empty set, right? So we use the same symbol, but conceptually, these are two different things. But there should not be any confusion about whether we are using a syntactic object, sorry, meaning a regular expression, or the set we want to denote. In fact, instead of writing the sets, we often use a regular expression that denotes the set, okay? And there are some conventions, as usual, in arithmetic for operator precedence. So this convention is that star has higher precedence than dot, which is concatenation, which is often dropped, by the way, or plus, and dot has higher precedence than plus, and we usually omit parentheses when there is no confusion, right? So let's take an example. Take this regular expression R, 0, 1 star plus 0. Okay. So what is the language denoted by R? Well, does it contain epsilon? No, it doesn't. But it contains uh, just the string 0. And all strings that have a single 0 followed by any number of ones. So that's the English description of this language. A single 0, any string consisting of this language contains all strings that contain a single 0 followed by a block of ones. And that block could be empty, right? How do we get this? Well, just use the definition. Because this plus is union, and the meaning of this star is Kleene star. So just use the inductive definition. And to do that, you'll have to follow these steps. So this is just L01 star union L0, and L01 star is L0 concatenated with L1 star union L0 is just 0, which is 0, and L1 star is sorry, this star should have been inside. If you look at the inductive clause for Kleene star, L1 is just a singleton, 1 star, right? Union. So that's what we just showed. So any question, any doubts about regular expressions and the languages they denote? Any comments, doubts, questions? Here's the definition again. On the left, we have the regular expression. On the right, we have the language of the set it denotes. Any doubts? So regular expressions are constructed out of the top 3 symbols, the empty set symbol, the epsilon symbol, and any symbol belonging to the alphabet, using the operations of plus, dot, and star. Okay, if you want to put it in words, right? So it's just like an arithmetic expression, except of course, the meaning of plus and dot are different, and star is something new. Yes? Any questions? Any questions about this example? Okay. Here are a few more examples. So 0 plus 1 star. Oh, by the way, there can be more than one regular expression which denote the same language. Okay, so for the same language, you can have different regular expressions, and probably we can see an example right here. So this thing here is a different regular expression. Well, sorry, no. I've just, I mean, sorry, this is the same regular expression which is written properly the way it is defined using parentheses, but we shall see examples later on. So these two are not different. I mean, it's the same regular expression where I have dropped the parentheses, right? But there can be two completely different regular expressions which denote the same language. So that's possible. We'll see examples later on. Okay, let's see. Let's just look at a few simple examples. So 0 plus 1 star. What would be, let's just assume that the alphabet is the binary alphabet. So what is the language denoted by this regular expression? Anyone?
So one concatenated with sigma star.
No. 0 plus 1 means the singleton 0 union the singleton 1, which is
a set of all binary strings.
Yes. So this denotes the set of all strings over sigma. Sigma is this binary alphabet, right? Okay. 0 plus 1 star, 0, 0, 0 plus 1 star. How would you describe the language denoted by this regular expression?
Any binary string containing two consecutive zeros.
Yeah, that's right. So this is the set of all strings over the same alphabet, 0, 1, with at least two consecutive zeros. You can even drop at least. I mean, with two consecutive zeros is just fine. Right? Let me see. 1 plus 1, 0 plus. Actually, plus is not part of the definition, right? I mean, you have 3D star, but you don't have r to the power or R superscript plus, but what we mean is what do we really mean here? Plus is just a shorthand here. What we mean is 1 plus 1, 0, followed by 1 plus 1, 0 star. Okay, so we can use plus as a shorthand in regular expressions, although it's not part of the official definition, right? I mean, plus is used as union, but not as a power or superscript, right? But as a this is just a shorthand. This one on the right. So this is you'd agree, is a regular expression. So what is the language denoted by this in English? How will you describe this language? And this exercise is not so easy. Figuring out the language which is denoted by a regular expression and expressing that in English is not easy at all, especially if you want a short description, okay? And I claim that this is the set of all strings this is the language denoted by this regular expression. Set of all strings with a 1 sorry, beginning with a 1 beginning with a 1 and not having and not containing two consecutive zeros. Okay, so this is not so easy to figure out, but you can check that the language denoted by the expression is indeed this language. Well, you can take a few examples, and of course, you can prove it, but I will not go into the proof here. But you can take a few examples. So the language here is a set of all strings beginning with a 1 and not containing two consecutive zeros. So 1, there is only one string of length 1. Epsilon doesn't belong to the language. What are the strings of length 2? Well, 1, 1 and 1, 0. These are the only strings of length 2. What are these strings of length 3? Well, it must begin with a 1 and it cannot contain 0, 0. So it could be 1, 1, 1, right? 1, 1, 0, 1, 0, 1. 1, 0, 0 will not be allowed. That's it, right? Is there any other string of length 3? And so on. Yeah. So you can see that the regular expression of all these strings 1, 1, 1, 1, 0, triple 1, 1, 1, 0, etc. They are indeed they can indeed be expressed by the expression 1 plus 1 0 plus. Okay. Yeah. So you can think of plus as this plus as a choice between 1 and 1 0, and this star or plus is an iteration, and the number of iterations, you can iterate as many times as you want. If you have a star, you can even iterate 0 times, whereas for plus you can iterate 1 or more times, and the choice is up to you, right? So using that process, you can generate each of these strings. So this is one way to think about that. Yes. So does it make it easier? Do you have any doubts about this? Okay. Let's see a couple of more examples. 0 plus epsilon followed by 1 plus 1 0 star, right? So this is the set of all strings of zeros and ones, of course, that do not have 2 consecutive zeros. So the language here is just the complement of 2, the language in 2, okay? It's the complement of that. Right? Again, it's not so easy to figure out why this is the case, right? So again, if you try to list all the elements of this language, you'll see that they are exactly the ones which can be generated by this pattern, which is the regular expression, okay? But not so easy to see. Yes, any comments, doubts? Questions? One more example. This is much easier. 0 plus 1 star, 0 0. Okay. So can anyone describe the language denoted by this regular expression in English? Set of all strings?
Ending with at least 2 zeros.
Yeah. Or you can just say ending with 00, right? Okay, right. So any doubts so far? As I said, it's not easy to figure out what the language denoted by a regular expression is. Um, uh, at least for some regular expressions, it's not so easy, right? But you can always work out the meaning of a regular expression by using the definition we have given. Okay, for every regular expression, there is a language which it denotes. So if you apply the inductive definition, you can get a language, okay? From that language to give a pithy English description is not so simple. And a description may not always, such a description may not always exist. Also, that is also the case. Anyway, so we have introduced regular expressions and the languages they denote. But why did we do that? Because we want to show the equivalence of finite automata and regular expressions. That's what we want to show. So the languages accepted by the languages accepted by finite automata are precisely, and it doesn't matter whether the automata are deterministic, non-deterministic, or have epsilon moves, are precisely the languages, because we have shown that they're all equivalent, denoted by regular expressions. So to show this, what we have to do is to take, say, a deterministic finite automaton and show that the language accepted by the automaton is also denoted by a regular expression. Okay. And conversely, given a regular expression, we can construct an automaton, right? Whether TFA, NFA, or epsilon NFA, which accepts the same language which is denoted by the regular expression. In other words, we can, given a regular expression, we can go to finite automaton. And given a finite automaton, and given a finite automaton, we can arrive at a regular expression such that the automaton accepts the same language as the one denoted by the regular expression. So let us state it formally as a theorem. And this is just one half of these translations, if a language L over some alphabet is LA for some DFA A, then there is a regular expression should I write small r's? I think I should write small r here just to be consistent. Small r such that L is denoted by R, i.e. L equals L of R. Okay. So is the statement of the theorem clear? So effectively, it says that given an automaton, a DFA, A, we can construct a regular expression, or rather there exists a regular expression, R, such that the language accepted by the DFA is the same as the one denoted by R. Okay. So if you want to put it in a few words, it's like given a DFA, construct an equivalent regular expression, where the meaning of equivalence is, it's easy to figure out. The language accepted by the automaton is the same as the language accepted by, language denoted by the regular expression. Okay. Well, I have just 5 minutes left. So maybe I won't be able to complete the proof, but let me start the proof at least. And this theorem is by Kleene. Okay, it was Kleene who showed the equivalence of DFA, or rather finite automata, and regular expressions. And this half of the translation, we are talking about this one here, from the automaton to regular expression. It uses a technique which you will come across later in your algorithms course, and that is known as dynamic programming. So in dynamic programming, much like divide and conquer, which you may have seen, you break up a large problem into smaller problems, and the solutions to the smaller problems are then put together to obtain a solution to the large problem. In dynamic programming, what you do in addition is the larger problem is broken up into a sequence of smaller problems, and the solutions to these smaller problems are stored in a table to avoid recomputing. And the solutions to the larger problem use these values stored in the table as solutions to smaller problems to construct a solution for the larger problem. Okay, that'll be clear. So this technique is used in, I mean, it's a well-known technique in algorithms, but Kleene used this technique for proving that you can go from an automaton to a regular expression, okay? So let A Q sigma delta Q naught. Well, we'll denote the initial state by Q1 here, just for convenience. F be a DFA where Q is Q1, Q2, up to Qn. So in effect, we just number the states from 1 to n, if n is the number of states in the automaton, right? This is a comma, by the way. Sometimes it's difficult to make out what is a comma and what is a 1. So this is a comma. This is a comma, right? Right. Then let R superscript K subscript IJ. Denote the set of all strings W such that W is the label of a path from Qi, from the state Qi to Qj in A and that path has no intermediate node QL with L greater than K, strictly greater than K. So in other words, this is the set of all strings W, which take you from the state Qi to Qj without passing through any state QL where the index L is greater than K. So that means all the intermediate states have to have their number less than equal to K. Okay, so I'll take up from here in the next class, and let me stop right there. That's the end of today's lecture.